everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland Joint PhD program. I am the TA for this course, Fundamental Laboratory Subject Science and Technology Fast. So let us begin today's class. So in the last class I have discussed some Fourier transform problem. And also how to measure like peak power, peak intensity, and from that electric field. And I have shown how to calculate not calculate how the pulses, these are the common type of pulses, the Gaussian. When you change from time domain to frequency domain, Gaussian remains Gaussian. How hyperbolic sect change, square pulse or rectangular pulse, and single-sided exponential function behave. The sec function remain sec, rectangular function remain sinc function, and so on. You can see the Gaussian pulse or hyperbolic sect pulse, when they change from time domain to frequency domain, they are with changes. And now starts class 6th class. First, let's start with the question at week 4, which I have done in the last class, but I made a mistake. The question was, what is the percentage change in the intensity of Gaussian pulse from t is equal to 0 to t is equal to 0.5 TFWHM, where WHM is the field full width at half maximum of the pulse. So the mistake I made, or sometimes it's easy to make, that we confuse between this field full with half maximum, and the expression function I t, which is not equal to, there are some coefficient involved, e naught whole square exponential minus 4 ln 2 t by tau f w h m whole square. Here we need to remember that this tau f w h m is intensity full width at half maximum. Now we are given TFWHM is filled full width at half maximum. So if TFWHM is filled full width at half maximum, then we know that filled full width at half maxima is 1 by root 2 times intensity full width at half maximum. So we need to take into account this fact. So half of t WHM is basically root 2 by 2 tau FW HM, which is 1 by root 2 tau FW HM. So we need to calculate the percentage change the intensity of the Gaussian pulse from t is equal to 0 to t is equal to half of filled full width of half maximum. So we need to calculate intensity at t is equal to 0. So that would be square exponential minus 4 ln 2 into 0, which is e naught whole square, and I f w t f w h n by 2, that would be proportional to e naught square exponential minus 4 ln 2 tau FWHM divided by 1 by root 2 HM, because this is basically 1 by root 2 tau FWHM. So this would be e naught whole square exponential minus 2 ln 2. So that is e naught square into 0.25. So the percentage change is equal to e naught square 1 minus 0.25 by 1, or we can cautious about which FW agent they are talking about. So now moving on, first let us remember some basic like mathematical expression like ET that was given by proportional to half of root over I of t exponential I omega naught t minus phi t plus Cc. This half factor and this complex conjugate factor, this is the real electric field to make this thing real. So for the simplicity of the mathematical form, we remove half and Cc factor. And also e to the power I omega naught t, we drop that thing. That omega naught t is carrier frequency, and when we would call omega naught the carrier frequency, the professor has already discussed in the classes, and I think there should not be any problem understanding the fact why it is called carrier frequency, why del phi del t is not called carrier frequency, and so on, and when then del phi by del t will be called carrier frequency. So then we have, if we drop this thing, we will have complex amplitude. And that would be E t equal to root over I of t exponential minus I phi t. So IT is actually intensity in temporal domain. IT is temporal phase. These things are all in temporal domain. Now we want to go to frequency domain. So if we take this thing that is exponential minus basically this is the this part's Fourier transform is this, and this is the Fourier transform of this complex conjugate part. So this is the Fourier transform of real electric field. So basically this is the real frequency domain electric field thing. And now we can consider that the negative frequency component contains the same information. This is the negative frequency component. Okay, they contain the same information as the positive frequency component, and we usually neglect it, and instead of and we also like put this omega naught is equal to 0 because omega naught is like almost constant, the carrier frequency. So this is the thing. So we write E omega, which is root over this thing, exponential minus I phi omega. So this is the complex frequency domain pulse field. So this is the frequency domain real field. This corresponds to basically not only the like this part. So this corresponds to real frequency domain field, and this corresponds to complex frequency domain field. And this S omega is called spectrum. And phi omega is called spectral phase. So now if you plot this thing in a double vertical plane, and in one direction this is spectral intensity, and in this direction this is spectral phase, and this is frequency. So basically this thing is E of omega. This corresponds to complex field, and this thing and this thing is eta omega. This corresponds to real electric field in frequency domain. So we only see this thing. To see this thing, and the phase corresponds to it like this. That is enough for us to know the full picture of the pulse. So the Gaussian pulse can be written as many ways. Can read is like E0 exponential minus t by tau half with whole square, or E0 remember tau half width 1 by e is the field width. Tau FWH is intensity full width at half maximum. The intensity is IT E naught square exponential minus 4 ln 2 p by tau FWHN whole square, or we can write it as exponential minus 2.76 p by tau FWHN whole square. So this is how we generally express the Gaussian pulse in electric field and the intensity field. Now here are thing called instantaneous angular frequency. Which professor has already discussed in the class how we get there. So that is basically omega naught minus del phi of d phi dt, where phi is a function instantaneous frequency. This is angular frequency. To make it instantaneous frequency, we need to divide it by 2 pi. Instantaneous. This is all in temporal domain. It will be nu 1 by 2 pi d phi by not d phi like d phi, but I was by mistake I was writing d nu, but it's not d nu, d phi by dt. This phi is a function of t, that means the temporal phase. And another thing has been discussed, that is group delay, and that have dimension of time, that is d phi. Here phi is a function of omega, that means fractal phase. So phi of t, this is temporal phase, and phi of omega, that is fractal phase. So I'll discuss more about what is group delay, what is GDD. Let us first discuss a question. So the bandwidth is delta nu, and there is an uncertainty principle stating that delta t into delta nu is almost equal to half. So delta t is basically pulse width, or you can say this thing. Not this thing, basically this thing. So basically when you say that femtosecond pulse, so basically delta t is of femtosecond pulse. So basically delta t is in 10 to the power minus 15 second range. So the slide given by the professor, here it was mentioned that delta t is 1 picosecond. So that is 10 to the power minus 12 second. So delta nu became half into 1 by delta t. So 10 to the power minus 12, yeah, fem but not necessarily in all problem of physics they are same. Problem to problem they got like vary. That's the thing that you should always remember. Here delta mu and del mu are the same, but this is not the case always. So then mu, which is we got 0.5 terahertz, and C is 3 into 10 to the power meter. We can like take it in meter or in centimeter. Here in the example they have taken it in centimeter. So this is 1 by second half and this is centimeter by second. So the basically thing it would have 17 centimeter inverse, and later what they have done that delta lambda inverse is basically minus 1 by lambda square into delta lambda. So we can take the mod, and so delta lambda would be lambda square delta lambda lambda for 800 nanometer wavelength. This is basically 800 to 10 to the power minus 7 centimeter whole square into 17 centimeter inverse. So this is basically 8 into 10 to the power minus 5 whole square into 17 centimeter inverse. So 64 into 17 into 10 to the power minus 10. So this is centimeter square into this is centimeter. So 64 into 17 is basically 1088 into 10 to the power minus 10 centimeter. So 1.088 into 10 to the power minus 7 centimeter, which is 1 nanometer. So you get to see that for a laser which is a wavelength 800 nanometer and pulse width is 1 picosecond, for that the frequency uncertainty is 0.5 terahertz or bandwidth is 0.5 terahertz, and delta mu is about 1 nanometer. So the bandwidth, basically the monochromatic light should be like this, but there is like it is like spread, not a spike. That defines that how wide is this spread. 800 nanometer is the frequency. So for 800 nanometer, so the thing can be 800.5 nanometer, also 799.5 nanometer we would get. It is not like laser sharp, like it is laser, sorry, we called something laser is sharp, but that the peak of laser is also have some width, and that is in spectral domain, not like spatial domain, not spectral. It is delta lambda is 1 nanometer. So we can discuss another question like this. Also, okay, also we can calculate delta lambda from delta nu directly. Basically, lambda is equal to c by nu, so delta lambda is c delta 1 by nu, so minus nu square delta nu, and nu is c by lambda, so c square lambda square delta nu, so that would be lambda square by c delta nu. So basically it is lambda square by c del nu, and if you put all this value directly here, you will also get, so basically it is 800 nanometer whole square, c is equal to 3 into 10 to the power 19 centimeter per second into 0.5 terahertz, like this is second inverse, so you will also get here 1 nanometer. So basically we need to remember three equation. Del nu del t is equal to half del nu is equal to c into del 1 by lambda, and del lambda is lambda square by c del nu, or it is lambda square delta 1 by lambda. Lambda is 64 by 3 into 10 to the power minus 8 meter. That is 21.33 into 10 to the power minus 8 meter. So this is basically 1 nanometer. So we can see that if delta t was 1 picosecond, delta mu was 0.5 terahertz, and delta lambda was 1 nanometer. We will see that when there is be 35 femtosecond, it would be something around 15 terahertz, and this will be something around 30 to 31 nanometer. For 5 femtosecond, the pulse duration is going down, like this is from this is going that, and you can see we got 100 terahertz and delta mu is around 230 nanometer. So basically in the temporal domain you compressed a pulse, but in the spatial domain it gets wider. So that was some basic thing. Now delve into there can be question about instantaneous frequency and group delay. So we know instantaneous frequency or angular frequency. This is instantaneous angular frequency. That would be omega naught d phi by dt, and this is instantaneous angular frequency. And this is angular frequency, instantaneous frequency, not angular. Right. So basically we know the same dimension can be added or subtracted. This is the basic rule. So the omega naught and d phi dt has the same dimension kind of thing. Always remember that. So if phi of t is a function of t square, so d phi dt is function of t basically, because the degree will reduce by 1. So basically basically if phi of t is a quadratic function of t, d phi dt will be a linear function of t. If it is a function of t cube, it would be the function of t square. Rocket science, basically the degree will reduce because there is a derivative. And same for that, like if instantaneous angular frequency varies is a function of t, then instantaneous frequency will be the same, because the factor is 2 pi and it will not change from t to something else. Like 2 pi doesn't have the power to change t to t inverse or t to the power 0 means nothing. So if instantaneous angular frequency is like function of something, most likely this instantaneous frequency will be the same function of t. Now you know the group delay is d square phi d omega. That should be the thing, that is group that is called GDD, that is group delay dispersion, and d phi by d omega is GD, is group delay. So if phi is, let's say, some function of omega, and that function is alpha beta omega plus gamma beta square, then group delay would be d phi by d omega. That is basically beta plus 2 gamma omega. That is group delay. And group delay dispersion, that is GDD, it is square phi d omega square. That would be 2 gamma. That is group delay dispersion. Okay. So if it would be gamma square, then it would be 2 gamma square. So the gamma is constant. It's like form, like gamma would keep it from gamma. It will not be like you cannot take a derivative of gamma with respect to omega, because you don't know if either gamma is a function of omega or not. And when you do not know, and it was not written in the question, gamma is constant, so no matter, gamma can be 2, so gamma square can be 4, so that is also a constant. If gamma is constant, gamma square is also constant, so gamma square would have been gamma square. Here it is gamma, the gamma would stay as a gamma. So even if, like, if it is a gamma square, it would like remain as this. Do not take derivative of that constant. And like there are some questions about positive charge, negative charge, and those things have been discussed in week 7 classes. If you go through it, and you will see it. And there is a question, if the frequency of the light wave is halved when its velocity remains the same, then how does the wavelength change? You can know that frequency is c by lambda, lambda is c by nu. If it becomes half of nu, so lambda becomes 2c by nu. So basically wavelength gets doubled, or if it is 1 by 4th, then it became 4 into lambda. So these are very basic things. Like actually it doesn't, like, you don't need fast level codes to answer this question. And there is question about negative charge and positive charge, like a non-dispersive medium. What would happen if the medium is non-dispersive and dispersive? So basically, like this things has been discussed in week 7. So I want you to go through that, and then I can discuss in the next class these questions. So I want to give you some basics of dispersion, like basic description of dispersion. What does this dispersion or group delay do to any pulse? That is the very important aspect of this course, or ultrafast optics. So to solve a question, like there is a question about what will be the relation between group velocity and phase velocity. So one of the relation between group velocity and phase velocity is this. So the medium is non-dispersive means that refractive index doesn't change with frequency. If it doesn't change with frequency, it means it doesn't change with lambda. That means n is constant, then d and d lambda would be what you know. Then just like solve the question, and you will get the relationship between group velocity and phase velocity. And basically, when the pulse is negatively charged, so the group velocity of some frequency is less than group velocity some other frequency. So basically negative charge means GDD is negative. So then what would happen? So these are the things. basically phi dash is the first order derivative of phi with respect to omega. Phi dash dash is basically second order derivative of phi with respect to omega, and so on and so forth. 0 is the zeroth order phase coefficient. Phi dash is called first order phase coefficient. Phi dash dash is called second order phase coefficient. Phi to the power n is basically nth order phase coefficient. For a very good pulse, you don't need to go up to 5 to the power n, but there are very bad pulses, as the professor explained in the class. Then you need to go beyond the second order thing. So if phi dash phi dash is non-zero, then first order dispersion will happen. And what will be the effect? The effect is that it will shift the pulse. If phi dash dash is non-zero, that means second order dispersion is there. So the effect is this term broadens the pulse. So we can see that first we see the first order dispersion. So if it is first order dispersion and it is greater than 0, so basically pulse shift in later times, and if phi dash omega naught is less than 0, pulse shift in previous time. So that previous times mean past and later times mean future. Basically pulse shift in right hand side, pulse shift in left hand side. Basically that is the thing. So we start with the frequency domain. So frequency domain I omega is I naught e to the power minus e omega minus omega naught. it will be 1 by 2 pi. This thing is not important what we are trying to like prove, but still okay. That would be e to the power I omega t e to the power minus I phi naught minus I phi dash omega minus omega naught, then a by 2 omega minus omega naught whole square d omega. So basically this term is constant in with respect to omega naught. We can like take it out of the integration part. So this thing is this e to the power minus I phi naught here. Now this is e to the power I omega t. So we need to match for the sake of simplicity. Have we should have at omega minus omega naught. So for that reason e to the power I, if we write it like this, we need to plus e to the power I omega naught t minus I phi dash omega minus omega naught minus a by t omega minus omega naught whole square. So this whole term can be written here to the power I omega naught t. This can be written as e to the power minus a by 2 omega minus omega naught square plus I t minus phi dash omega minus omega naught. Okay. So you can write this as e to the power minus alpha x square plus beta x dx. Okay. So basically omega minus, here it is d omega so basically omega minus omega naught is x, so d omega is dx. Alpha is a by 2, beta is I t minus phi dash. So we know that minus infinity to pi minus alpha square plus beta minus alpha x square plus beta x is root over pi by alpha beta square by 4a, not 4a, it's 4 alpha. domain, we have a we had a intensity, we had a corresponding spectrum or electric field. I should not call spectrum. This is E omega is electric field. Basically here I omega you can corresponds to spectrum. So when you like Fourier transform, you can see that you are doing only Fourier transformation, just taking the Taylor series expansion of phi, which was here, the phase part of phi, and took up to the first order differential equation. When we do the Fourier transform and like get back to in the temporal domain, you can see the time pulse has shifted from 0 to on the right hand side. So basically only the pulse has been shifted. So it has shifted in the positive time domain. So that is the effect when you consider group delay. Now what will be the effect when we consider group delay dispersion? That is again non-zero. So I omega, it is spectrum, you can say I naught e to the power minus 2a omega minus omega naught square. So E omega would be something not e to the power minus a omega minus omega naught whole square e to the power minus phi of omega. So I put a proportional sign because there is basically many constant involved, whatever I have written in the first. Okay, so there is a question because I have written some nothing. I just say that this whole thing is here, and I also put e to the power minus phi naught is also here, but why didn't I put omega naught in that bracket? Sorry, this should be omega naught, otherwise whole integration will collapse, because this is carrier frequency. It is important. It is very important. So okay, this time phi omega gets phi naught plus phi dash omega minus omega naught plus phi dash dash 2 factorial omega minus omega naught whole square. So we will consider up to this. So basically E omega became I naught e to the power minus I phi naught minus I phi dash omega minus omega naught minus I phi dash dash by 2 factorial, or 2 is the same thing. 2 factorial is 2 omega naught square minus A omega minus omega naught square. Okay. So basically this part says that we are taking Gaussian pulse. So there is a constant pulse, constant thing, and there is a Gaussian part. So this thing ensures that we are taking Gaussian pulse. So we started with a Gaussian pulse which is centered at omega naught. So even omega naught is equal to 0, this carrier frequency part goes to 0. There is no omega naught here. So the pulse will still shift. So that's the point of the whole thing. So this is the case. Now you want to have a Fourier transformation, which would be 1 by 2 pi minus infinity to plus infinity e omega e to the power I omega t d omega. So that would be 1 by 2 pi root over I naught minus infinity to plus infinity to the power minus I phi naught minus I phi dash omega minus omega naught minus I phi dash dash by 2 omega minus omega naught whole square minus A omega minus omega naught square into, that's not it. For the Fourier transform we need 1 I omega t dt. The same thing here, we need to convert omega to omega minus omega naught, so we will multiply with e to the power minus I omega naught inside the integration and keep the I omega naught t part outside the integration. So basically that would happen I naught by 2 pi like previous thing. We got this thing out, so we'll get I omega minus omega naught t minus I phi dash omega minus omega naught e to the power minus A omega minus omega naught square minus I phi dash dash by 2 power minus I omega t minus infinity to plus infinity. We call it e to the power minus alpha omega minus omega naught whole square plus beta omega minus omega naught t omega. So this thing is this, okay, so this is positive, where I omega naught t and here it would be pi. So here alpha is basically a plus I phi dot t and beta is basically I t minus phi dash. So that becomes a plus I sigma dash by 2 e to the power minus t square by 4 a plus I sigma phi dash dash 2. So now we'll do the calculation here. So this thing is this I omega naught t, okay, this phi guess it remains the same, e to the power minus t. We will try to do this thing, phi dash dash by 2 whole square into a minus I phi dash dash by 2. Now this thing, that thing, this is that, this is that, e to the power I omega naught t, can write it as 4 a square plus sigma dash dash square by 4. Here we can write it as a t minus sigma dash whole square, and there we can write it minus minus plus I sigma dash dash by 8 a square plus sigma dash dash by 2 whole square t minus sigma dash whole square. So you can see there is a I, this is I. So this part is phase part, and this is because of the Gaussian pulse. So this is, you can write it as minus t square by delta t out whole square, because t in was different thing, and this is I omega t plus I phi dash dash. We can say t square because phi dash is very small, by 8 a square plus phi dash dash square by 4. So the phase part has now a linear part and a quadratic part. This part is linear and this part is quadratic. new phase, total phase here. This is omega naught t plus phi dash dash t square by 8 a square plus phi dash dash square by 4. And delta t out is 4 by a s square plus sigma dash dash square by 4. So this is the broadening part. So because delta t in would have only a square, so delta t out is less than delta t out. That caused the broadening, and phase has now a quadratic part. That is the effect of GDD in the equation. So there is a formula, delta t out is basically what happened is delta t in square plus 4 ln 2 sigma dash dash delta t in whole square. That is what happened naturally. So for Gaussian this happens. So you can see how broad the pulse can be depending on delta t in. So this is delta t in, this is phi dash dash. So this is 100 femtosecond square, this is 200 femtosecond square. Okay, so for if delta t in 5 femtosecond and f dash dash is 100 femtosecond square, so 5 femtosecond becomes 55.7 femtosecond. And if sigma dash dash is 200 femtosecond square, that becomes 1111. And if this is the case for 20 femtosecond, this is 24 femtosecond and 34 femtosecond. The similar case for 80 femtosecond. Is 80.1 and 80.3. So you can see that when the pulse is very short, the group delay dispersion can affect in a very much broadening. But when the pulse is comparatively broad, the broadening is very less. So this is for today's class. I will discuss other things in the next class, like how the prism and the grating can compress or decompress the things, and maybe the professor also will discuss these things. So see you in the next class.